Swinburne University of Technology.
Okay, thanks very much for that, Arm. So as Arm said, my name's Luke. I work for Swinburne University in the astronomy department. So my my role is generally to support high-performance computing in the center, and I'll be talking today about software testing. I think it's one of those things that can easily be overlooked when it comes to designing software, especially in research. I think it's got a sort of a bad reputation for a number of reasons, but I think it's quite important, and it's something that I've found to be incredibly useful over my time developing software. So the focus will be, for the most part, on C and C++, with a little bit of Python in there. Hopefully everyone's familiar with one of those two languages. It'll certainly help a lot. So I found myself quite often repeating phrases similar to these ones, which became a source of frustration that needed to be solved using a more structured system. So I'd find myself saying things like, "It was working just last week," or maybe, "I only made a very small change. I don't know how it could have possibly broken something that wasn't even that connected." Or I'd say things like, "I'm sure this has been fixed before. How come I'm fixing this again?" And these are all signs that software testing could be something lacking from the project, and something that can certainly help prevent these sorts of phrases cropping up in your development cycle. So one of the things that I think testing perhaps is a bit of a myth about testing is that it will end up costing you more time than it's worth. But I think in the long run, with a broader scope, you'll see that testing can actually save you quite a lot of time as opposed to consume it. Something testing can do if used from the beginning is to not just identify problems in a system that you're developing, but it can also prevent problems right from the beginning. I'll talk a bit about that nearer the end. Something that's perhaps not quite so obvious from the beginning as well is that testing can make your code more attractive for others to use. If testing isn't implemented in a piece of code, it becomes difficult to consider it reliable. And when working in a team environment, it's pretty obvious that a good suite of tests can make preventing errors finding their way into a code base a lot easier. So this is a fairly, well, somewhat indicative, just a high-level description of what a lot of projects might look like, especially smaller projects. You may have, at the bottom level there, a library that you've developed for use with a particular application. And then perhaps, at least at the beginning, while the application's quite small, you might consider a good testing regime to be to provide it with a certain set of known inputs, produce a set of outputs, and then just look at the outputs to determine whether you think everything's working correctly. And it does work, and it works as long as there's not too many outputs that need to be checked, and you can get some reasonably good results just with something simple like this. But problems, I think, start to happen when you have this library that you might use for this one application you were using, like that. But then perhaps you might have some other library that you're working on that might take out some components from the bottom level library. You may even have another application built on top of the second library that you're developing. And then perhaps you might go back and make a modification to the original library. And now you've got a system where, in order to verify that you haven't broken anything in any of the other levels, you may need to produce a whole suite of outputs and then spend a certain amount of time eyeballing each of the results. And if you continue this method of validating your code, it can eventually lead to an awful lot of time spent just from making very small modifications to a lower level of the system you're working on. And at the end of the day, we really want to automate as much of this procedure as possible to shift the time from the time you spend debugging to actually doing development. Another good reason for some thorough testing structure is if anyone's ever used a supercomputer, which these days has vastly parallel technology, with insufficient testing, you can end up spending quite a lot of time just making sure it works. And when you've got a certain amount of grant time on a machine like that, you really don't want to be spending all of your time just making sure the code's running. You want to be spending your time making sure that you're getting results. So it's very, very helpful to have as much of the code very confident in its ability before you end up trying to port it to a larger parallel machine. And obviously, when you have multiple people using the same source, so a certain repository of software, when you're not making all of the changes to the code, it's very difficult to look at the output from the code and know it's correct. So having a system where other users can write their own tests for the parts of the code they're working on, and then you can go ahead and validate that any changes you've made aren't causing any problems with the implementations they've created. I mean, it's quite clear that how useful that can be in a situation with many developers. And I quite like this quote in terms of explaining code attractiveness. And this is from someone from the Django development team, Django being a fairly large WebKit system. And the quote is, "Code without tests is broken by design." And I think that's something that a lot of developers, a lot of software engineers consider to be true. And when looking at libraries and other pieces of code that they might want to use, if it doesn't come with a suite of unit tests and various other tests, it's less attractive to be used in these in their own projects. So I've talked a little bit about the motivation behind including some testing. So now I'll start by talking at a bit of a higher level about the different kind of testing methods that you can employ to make your code, give it a bit more structure with its testing environment. So I think you can broadly decompose the testing arena into two different categories. The one on the left is static testing, and the one on the right is dynamic testing. So there I'm talking about whether you're actually running the program you've created to see if it's performing the way you're expecting. And the static side is analyzing the code itself, the software that you've written without running it, to see if it's to verifying that it's fulfilling the requirements that you've set upon it. So inside of the static category, we have things like reviews, walkthroughs, and inspections, which they're all subtle variations on the same concept of essentially just looking at the code. So opening it up with one or more people and looking through each part of the code and making sure that there's nothing wrong, which is obviously not the most robust way of examining for errors. And then you have IDEs, so things that will try and identify syntax problems just by having their own internal irregular expression systems. And the last one there is static analysis. And static analysis is actually quite useful, but again, it's something you do without even actually running your code. I'll talk a bit more about static analysis later on. So in the dynamic category, we have functional and non-functional testing. So functional testing is actually making sure that the functions, the code that you've written, does what it's supposed to do at a very Boolean level. So it's, does it work or does it not work? And that sort of includes a whole range of testing methods that we'll talk about, unit testing, integration testing, and so on. And on the non-functional side of things, we have the kinds of tests that aren't really yes or no, but are more sort of more difficult to describe that way. So we have performance. So I mean, performance can fluctuate. We have usability and security. So these are all things that I won't cover in this talk, but they're still quite important. So I think these are the main things I'll try and cover. So static analysis, unit testing, integration testing, system testing, regression testing, and sanity testing. So I'll talk a little bit about a certain approach now that is quite useful in thinking about how to design the tests that you might want to include with your code. It's called the box approach. And essentially it's just a way of viewing, describing the point of view of the tester that's going to be designing these tests. So in black box testing, what we essentially have is an idea about the interface, so the inputs and outputs that a certain module of the code might use, but we don't have any idea about the implementation. So that's hidden from us. So the question is, what kind of tests can we write with this sort of an approach? So for an example, I'll just use a Newton-Raphson solver. It's nothing too complex, but the internals at this point don't really matter. What we have is something that's going to try and find the point at which a function is 0, and its inputs are the function we want to find this for, the bounds inside of which the solution should lie, the initial guess, and then we have some parameters like the tolerance, so how accurately we want it to solve, and we have a limit on the number of iterations that we'd like it to adhere to. So just from this interface, using black box testing, we can design a few potential tests that we could check for. I mean, we could supply it with a number of functions that we know answers for and check that they're okay. We can check variations on the lower and upper bounds and make sure that's all right. We can check for different variations on the initial value. We can modify the tolerance and the maximum iterations and see how that affects the results. And these are all well and good, and they're useful in a lot of situations. But we can do better by using white box testing. So in white box testing, we not only have access to the interface, but we also take into consideration the implementation of the module that we're testing. And this is quite useful because now we don't just have to design our test based entirely on just the inputs and outputs. Now we can take a look inside and really customize the test that we might write to try and make sure that everything we're interested in validating is indeed validated. So for the same example, we may look inside the implementation of this Newton solver, and we may see that it uses a scaling to make sure that if we were to pass in a very, very small value of the initial condition, the initial value that we're after, it's not just going to converge immediately because that value is close to 0. So it may scale that and use that scaling factor later on to augment our iterations to make sure that we converge correctly. So this is something that we'd actually want to test to make sure that this works. So white box testing lets us write more thorough tests to make sure that the thing we're checking is really well tested. So in this case, we may wish to also check that the small scales converge correctly, and also with larger scales. And also a fringe case there where we might want to check that if we pass in 0, we don't in fact get a divide by 0 error, that everything works the way we would anticipate it to. Of course, especially if you're coming into a project afterwards, after a lot of the modules have been written, white box testing can be pretty daunting. There may be an awful lot of code and an awful lot of branches in the code to have to consider. So it may not be worth the time, or you may not wish to spend the time testing things that perhaps aren't that important. So the last level of testing is called Grey-bax Testing, where it's essentially just a somewhere in the middle. So you have the interface. You could be aware of the implementation. You may not want to step through the implementation one line at a time and make sure everything's tested as much as possible. But you may have some idea of how the internals work, and you can design your tests to try and capture all of that without going overboard. So I'll take a look at static analysis now, which is, I guess, what I would say is the first port of call for testing your code for certain problems. As I said before, this is something you do before you even run the code. This is something you can do just with your source files. So I'm sure we're all intimately familiar with the kinds of compiler errors that you might see when writing a piece of code. Actually, before I get into static analysis, I'll just ask if anyone's got any questions about what we've gone through so far. I'm not too familiar with the system we're using, so I think you can put your hand up somehow in the and ask questions. But oops, sorry. No, I can't see anything, so I'll keep going. But I think you can just raise your hand in the or type messages at the bottom of the control panel. So I'll continue with static analysis. So yeah, compiler errors. I'm sure we're all intimately familiar with the kinds of compiler errors that you might get from compiling code. I mean, you'll get parse errors if it can't even interpret the text in the file, and syntax errors. There could be missing headers, symbols. You may have trouble finding packages and libraries. Sorry, just getting a test question coming through. Thanks, Greg. Cool, it's good to know that that's working. Okay. So yeah, and you may also get certain compiler errors, warnings even telling you about certain numerical issues in the code. And they're all very helpful, but there's a certain array of issues that compiler errors won't tell you about. So, for example, it won't tell you if you're going to access an array out of bounds. It also won't tell you about returning pointers to variables that may no longer exist. It won't tell you about dereferencing null pointers, and also there's a whole host of other logical problems that won't be captured by... Actually, I can just see someone's got their hand raised, so if you'd like to ask a question, please go ahead. Sorry, this is for Mohammed. Sorry, Mohammed. I think if you've got your hand raised, we've just opened your mic. So if you'd like to ask a question, please do.
No, I don't have any question. I was just checking the.
Oh, the hand.
Yeah.
Yeah, cool. No worries. Great. Thanks very much for that.
Thanks.
Good. Well, at least we know the hand raising is functional. Okay. So there's lots of, as I'm sure everyone's aware, there's a whole host of logical errors that can find their way into source code, and it would be really handy if we had some mechanism to help us also provide error messages when these things happen. So one such tool that I've found in the past to be incredibly helpful is a thing called CPP check. So that's its URL, and this piece of software can essentially, like a compiler, provide a whole host of warnings and errors for logical problems. And these are just a few things that from the website it claims to be able to check for. And it does a pretty good job, I must admit. It's certainly caught a fair few silly logical errors I've included into my code in the past. So it's one of these things that I don't think is that commonly known, but it's really very useful. So as an example, I've got a little piece of code here that does a couple of these silly things. So for a start, so the first function there, all it's doing is taking an integer and trying to convert it to a string. But what you may notice is that the first thing it's doing is the buffer is of only size 3. So this string that I'm printing into it is quite clearly going to run over the end of that buffer, which is something, I mean, a later C compiler may actually pick that up as a warning, but earlier C compilers certainly would not. And the other thing this piece of code is going to do is return a pointer to this local buffer, which in fact is going to end up being garbage memory. So when I try and print it out in the main function, that's just going to give me nonsense. So when I run it through CPP check, it picks up on both of those things relatively easily. And it gives nice descriptive errors of the problems it finds. So, I mean, this is, as I say, before you've even run the code. So this is very, very useful for ongoing development. And later on, I'll talk a little bit about how to automate these kinds of checks. And the difficulty, unfortunately, with most interpreted and dynamic languages is they're vastly more difficult to do these kinds of checks. So what we do have a few packages, or there are a few packages available for doing static analysis of Python code. They're not very well established yet, and they don't pick up a lot of problems, and they're useful more than anything for making sure you're adhering to a coding style that you may decide upon. But they're not really going to give you too much information about logical errors. But if you're interested, PyLint is probably one of the better ones. Sorry, just checking for hands being raised. And I think we have Puria, do you have a question? Sorry, just making, I'm not sure I'm pronouncing your name correctly. Is it Puria? No, can't hear anything. Ah, yes. Do you have a question? Oh, there. Sorry, I see it. Right. So I know that NVCC has beg your pardon. Oh, sorry. Of course, I'll repeat the question. As I understand, not everyone can see it. So Puria asked, unfortunately, I don't have access to microphones. She's asking whether such a thing, a static analysis checker, exists for NVCC. And the answer is, I don't know precisely whether there's a static analysis tool, but NVCC does have its own flavors of other analysis tools like Valgrind and GDB. And Valgrind especially does a very good job of identifying memory problems. So the short answer is I'm not sure about static analysis. Long answer is there's certainly a host of tools that are very useful for NVCC. I hope that answers that for you. Are there any other questions coming up? No. Okay. So I'll move on from static analysis and talk about sanity testing. So sanity testing is sort of like in the range of actually running your code. So in the dynamic testing category, this is sort of like the very lowest level you could imagine. It's if it's basically checking for if something horrifically wrong has happened and whether we should even continue bothering to run tests or whether we should just stop. So the base level mechanism for something like this is called an assertion. And essentially all an assertion does is check for an expression. And if it's true, you continue running. And if it's false, you abort the entire run straight away. And it aborts it at the lowest level, so it uses signal handlers to flag the code. So no matter what's happening, it'll just dump straight out. So yeah, it's a pretty crude method, but it does have its advantages. So for a start, it's incredibly simple. It's just a single one-liner. You can put it wherever you want. It's very, very easy to use. It's already provided. It's already out of the bag there for C and C++ and Python. And it's also optimized out at the end. So you can have as many of these as you like. When you go to produce your production code, none of them will be there anymore. So it can make sure it's still very fast. And of course, the disadvantages, you don't get much information. I guess that's part and parcel with being very simple, is that it's limited in the amount of information it'll provide. And it's not really a test suite. So it's not something that you can have a nice progressive display of how well things are going. It's really just littered throughout the actual code and just telling the code to stop even running if something goes wrong. So here's a very simple example. So if you're allocating a bunch of memory for a string perhaps in C, and in hindsight this may not have been the best example because an assertion is probably not what you want to use here, but it illustrates the point. So if the allocation fails and you return a null pointer, that's not something you really want to happen. And if it does happen, you certainly want to be aware of it. So you can throw an assertion in there just to check that the return pointer isn't null. As I say, you probably want an exception in there or some other method of handling it, but it just illustrates that assertions, they're just used for stopping insane things from happening in your code. And as I said, these are the sort of things that you might want to put all the way through your code in a lot of different places, checking for potentially long checks. So in the C compiler, the assertion header comes looking something like this at the top there. So basically, it's wrapped inside a preprocessor definition, which so if ndebug is not defined, the assertion continues on existing and does its checks and aborts if the check is false. But if you do compile your code with ndebug as a preprocessor flag, then the assertion evaluates to nothing. So it's really good for pieces of code that are highly optimized and need to make sure that something's not breaking in there, but you also want it to remain highly optimized once you've finished checking for these sanity tests. So you can see here that you can compile your code in a debug mode and an optimized mode to switch on and off these assertions. So I find these things to be incredibly useful, and I use them everywhere. And I do higher level checks as well. So I might test that a certain complete set of objects contains certain values on every object. So the assertions can take a very long time in debug mode, but yeah, you can strip them all away later on for the optimized final product. They also exist in Python. So Python has a built-in keyword assert, and you can also run your Python code with a flag that tells it to get rid of those assertions as well. So here I'm just doing a couple of checks. And at the bottom there, you can see that Python's assert goes a little bit further, and you can also print out a message along with the assertion. Unfortunately, C doesn't have the same capacity. So I'll move on now to a bit more of the meat and potatoes of testing. So unit testing, integration testing, and system testing are really the primary elements of making sure that your code is thoroughly tested. So I'll just go over these sort of levels from the most basic level working upwards. So unit tests really focus on making sure that essentially 1 + 1 = 2. It's testing the smallest sort of accessible unit of your code that you have available. In unit testing, you'll tend to use all three: black box, white box, and grey box testing. They're all quite commonly used for unit testing, although I would say that white box testing is probably the most common of the lot. So in integration testing, we're taking the individual components that we've tested with unit testing, and we make sure that they play nicely together. So it can be a little bit more complicated to work with, and perhaps not quite so clear-cut, but so you end up using things like perhaps black box or grey box testing to facilitate integration testing. And system testing essentially takes the entire finished product and makes sure that the runs from beginning to end produce the output that you're expecting. Regression testing, which to be honest I'm not sure belongs in the levels, the testing levels. Regression testing is a way of ensuring problems don't work their way back into your code. So if ever you find a bug in the code with regression testing, you'd be sure to add that to the list of suites, the test suites that you run through. So let's take a look at how unit testing would work. So if we happen to have a few classes, C++ classes perhaps, or Python classes, so we have class A and class B, which are independent. They have their own set of methods that operate only on themselves. And we have class C, which is some other class which makes use of both class A and B. Then unit testing would be mostly focused on the standalone functions and methods and making sure that they do what they're supposed to do. So we'd be testing class A and B more specifically. Class E would be saved for integration testing. And these are the concepts that we'd really like unit testing to fulfill for us. So we don't want to spend, well, we'd like to spend as little time as possible writing these tests. So we really want them to be easy to implement. It would be very helpful to have some high-level descriptive information about the failure, and if we can, some low-level information. We really don't want to have to repeat the same code a lot for writing each of these tests, because there could be quite a lot of them. And ideally, we'd like to have the flexibility to send the results of the tests to different consumers. So we may want to have a website where we display passes and failures. We may just want to display it at the console. So a bit of flexibility would be useful as well. So as an example, we have a C code here, which is just a complex number, so a real and imaginary part, and we've added some arithmetic to it, so addition, subtraction, division, and multiplication. So we'd like to write some unit tests to make sure that this is doing what we're expecting. So the first thing we could do, which is sort of the ground floor of unit testing, is just to write our own program, and in there use some assertions to check that the operations we're performing are coming up with the numbers that we expect. And this does work. It'll tell you whether something's not working, but unfortunately, it doesn't really fulfill a lot of the concepts we wanted. It is easy to implement, and it doesn't have much boilerplate code to go with it, but the failures are not very descriptive at all, and it's incredibly inflexible. So to try and solve the descriptive failures, we could start adding printfs inside each of these checks. But while that does give us some descriptive failures, unfortunately, we're now getting a lot of extra boilerplate code in there, and it's still not very flexible. And while I could go on talking about how we could build up our own unit test system to do this, of course, it's already been done by a number of other groups before. So here's a few of the different options we have for C unit testing. So CPP unit and CXX test are two of the bigger ones. They're very feature-rich. And CXX test actually has a very nice feature where it uses a Python script or a Perl script to automatically identify all of your test code. So you don't even have to write any test runners or anything. It'll pick up a lot of that for you, which is really good. However, my personal favorite out of these is Catch, which gives you a very similar level of minimum boilerplate, but also has some very clever code to make it very easy to print out highly detailed information about the failures that your unit test may be having. So that's the one I would certainly recommend. So let's take a look at what unit testing in... Oh, sorry, I've got a question. Sure. So the question was whether these were C or C++. So all of them are C++, but also, in addition, all of them are usable with C. There are certainly C exclusive unit test frameworks. I like these ones, or I mention only these ones because they do provide a really high level of minimum boilerplate. So it means a minimal amount of effort to get a lot of information out. Sorry, do I click on the... Yep. Okay. So looking at catch for the complex numbers test, what we're doing here is including the catch header, which is all we need to do to tell the code that it needs to be runnable. We define each test case with a macro and give it a nice descriptive name. Inside the test case, we treat it just like a function. So we set up our data, we have a few complex numbers, and then instead of using assertions, we use a macro called require, which essentially just does the same thing as assertion, but also adds a whole host of nice information in the background. So those things are the magic behind which all of this nice information gets stored. So this is what it looks like to run a catch unit test suite. So with the minimal output, we end up just getting essentially a summary. So it'll tell us that all tests passed or if something didn't work. The same thing run with the verbose output gives us the name of the C file that we're running, whether everything, all of the tests that passed, but also one thing which I think is very clever, and it uses a bit of clever C++ operator overloading. It'll also tell us the contents of the variables that it evaluated. So we also get the internal values of the complex numbers that it's comparing, and I think that's nice because typically with other unit test suites, in order to do something like that, you end up needing all of these test assertions. We have all of these different ways of telling the unit testing suite what kind of things we're comparing. So whether we're testing for equality or whether we're testing for less than or greater than. And the nice thing about catch is it only needs one of those. So just using require, we can get all of the same level of flexibility just with one keyword. So it's not much to remember, and it's really nice, I think. And this is what it looks like to have some failed results out of that unit testing framework. So it gives us information about where in the test suite it failed. It tells us which line it was and the contents, again, of the variables, and also a summary at the end. So it's certainly giving us enough information to begin looking at what's failing. And in terms of flexibility, it also gives us a thing called reporters. So they have a few built-in reporters. This is the output from the XML one. So with no extra effort on your behalf, you can also get out a file which contains all of the results from the unit test suite. You may, for example, want to send that file to a web server, which would then present that information to your development group. So it's flexible in how it produces the information about passes and failures. So it's the catch unit testing framework, but I should also say also the others. The others also fulfill these requirements, but I do feel like catch has done it in a very elegant way. So it would be my recommendation for C and C++ unit testing. So one thing that anyone who's written unit tests before can attest to is that quite often you have an awful lot of common code that would be nice to be factored out and be used across a whole bunch of unit tests. So if, for an example, say we have a little piece of code whose job it is to parse an input file and store some results in an information structure. So at the moment in the information structure we just have param A and param B. And the parse function just opens that file, reads in a bunch of stuff, and parses the text and stores it in that info structure. So if we wanted to unit test this, here's some of the possible ways we'd do it. We'd perhaps check for a missing file, check for an empty file, and then we might want to check that param A and param B are getting parsed in correctly. So if we wanted to test param A, one thing we might have to do in the test case is open a test file, write out a set of test data to the test file, close the file, and then parse that file and use the require test assertion to make sure that the numbers we're reading in are correct. And that's a reasonable way to check it. But of course, for the exact same, a lot of the exact same code would need to be used to also run the test case for param B. And that's going to get old very quickly, having to duplicate the same code in potentially a lot of different places. So most unit testing frameworks have a mechanism called Fixtures to help prevent this sort of thing happening. So we can take this code that we have that's common to probably quite a few unit tests, and we can put it in a structure. This sort of thing can also be done with C, but it would be using function pointers. But it's just a little bit nicer in C++ to use a constructor on a class or struct object. So here we can see that we would be we'd be creating a file, we'd be storing the file name and filling in all the contents just in this constructor, which means we keep all this code in one place, which is a nice way to do it, and it'll get executed each time we run the unit test cases. So you can see here that the catch unit test framework has a different variation of the test case macro, test case method, and this one accepts the fixture class and runs the test case, the contents of the test case, as though it were a method on the fixture test, the fixture class. So you can see in these tests I'm using fn for the file name and info directly off the parse fixture, which cuts down the amount of boilerplate needed to run the same test on these test cases that we're writing. So it's a nice way to cut back on boilerplate. So Python also has a few different unit testing mechanisms. There's the unit test and doc test, both of which come with Python out of the box. Doc test is an interesting one. It essentially keeps the unit test that you write as comments in each function. which is nice in a way. It certainly makes sure that all the tests you write are bundled with the functions, but it's perhaps a little unusual. And then there's an external unit testing framework called Nose, which is essentially the same as unit tests, but goes a long way to eliminating a lot of the extra boilerplate that you may need to write. So I have a tendency to use Nose for my Python unit testing. So just quickly, this is what it would look like to set up a generic unit testing suite for Python. So if you happen to need fixtures, you just declare them as functions in a single file. In the same file, you can use a decorator mechanism to supply the setup and teardown functions for the fixtures. So the teardown function being just a bit of cleanup that may need to be done after setting up the fixture. And the thing about the Nose unit tests is that as long as you prefix your test name, your function name with the word test, it'll automatically detect it. So you don't have to do any other work than this to have the entire framework locate all of your unit tests. So if I were to create a file like this and then put it in a directory and just run the command nose tests, the nose tests would use the automatic discovery system and walk through my code base, find all of my unit tests, and run them all for me. And this is just a minimal successful output result. So the Python nose test framework also gives you some information about failures. It can actually give you an awful lot of information. I had to strip back quite a bit of it to make it fit in the window. But yeah, suffice to say that there's no shortage of details when a test fails. So I'll talk about integration testing next, which, as I mentioned earlier, really is now talking about taking the things that we've validated with unit testing and making sure that they now work together. So we'd be looking at things like Class C, where it makes use of two of the previous classes that we've checked. So let's take a look at combining the complex number system with the Newton solver, which we looked at earlier. So if we were, for example, to use just a function like this, so what we're doing is telling the Newton solver that we're going to try and solve a quadratic function, so x squared minus 4. If we pass that in to a test case, so we set up some complex numbers and the function we just talked about, and we check that the results that we get from running the Newton solver with complex numbers delivers us the results that we're expecting. So you can see that the implementation is actually very, very similar, and in fact identical to the unit testing mechanisms. But in this case, we're just making the distinction that in these cases we're looking at the interaction between other components. And system testing, again, is similar to integration testing, except now we're taking it one level higher. And we say that we have the finished system that we're interested in testing. The implementation is most likely no different to unit and integration testing. I guess the differences would be that you'd likely use some fairly complex fixtures to set up the input environment, say, for example, generating input files. And you may also need some complex correctness measures. So you may need to use things like linear regression to make sure that you're getting reasonable results, or you may need to have some form of other approximate comparisons. It may not be as clear-cut as 1 + 1 = 2 in this case. So there are some other tests that you can use, perhaps not so common as unit tests and integration tests, except for possibly regression testing. So regression testing, as I said, is just a method of making sure errors don't find their way back in. So whenever you find a bug, or whenever a bug is reported, you'd simply want to add, before solving the bug, add the conditions for reproducing that bug to the unit test suite, so that way you'll always be checking into the future that particular error doesn't find its way back into the system. So smoke testing is similar to sanity testing, the difference being that it works on higher level components. So if you have a high level modular system, you may just want to run a very, very simple set of inputs through that component just to see if it breaks horribly. And the term smoke testing actually comes from testing electrical circuits, where you just switch the circuit on, and if it starts to smoke, something's wrong. You can also do destructive testing, where you actively attempt to break your components. So you may send in a set of inputs which you know is wrong, and you just check that the code either handles it gracefully or does actually catch the situations where these sorts of problems turn up. The final one that I think bears mentioning is installation testing. So this is useful if you know you're going to run your code on perhaps different hardware configurations. And for supercomputers, I think that's something that does happen. So it is nice also to have a mechanism for checking that the code does install and run on hardware configurations that you did not develop it on. Are there any questions so far? Yes, there seems to be. That you could be right. I actually got the that quote of the electrical testing. Sorry, I'll just say that someone's mentioned that they think that smoke testing was plumbers passing smoke through a pipe to make sure no smoke escaped before hooking up the water, and that you could be absolutely right. The quality of that reference for me came from Wikipedia, so it's entirely possible that it was an example of Wikipedia feeding me bad information. But either way, I think the general gist of just doing a very, very simple test to make sure that something doesn't explode horribly is the idea there. Right. So all of these tests, all very good and well. But if you have to run them all manually, one at a time, it's not that useful in the end. It's what's really needed is a way of automating this procedure. So not automating writing the test, but automating running them and examining the output. So there's two very simple ways to do test automation. There are more complex ones, but just from a basic level, the options we really have are to take all of these tests and lump them all into one piece of source code and compile that one binary and then run that test and just have the test binary, which is very simple, but perhaps not a great idea. It may not be the most feasible thing to have just one giant binary in your system being built. So the recommendation that I would have is to use build system integration to do this. So augmenting whatever build system you may use to assist in running all of these tests for you. A lot of these unit testing frameworks actually do come with scripts to help you do this, depending on the build system that you use, of course. So the most common build system being Makefiles. This is the kind of thing that you would be looking to do, and it's not that complex to do if you've seen a Makefile before. So, for example, if we have targets on the left, so test complex, test Newton, and test Newton complex being our unit testing binaries. We may also wish to add a target in the Makefile called check. And check's kind of, as far as I'm aware, it's the sort of common name that a lot of software uses to identify the unit testing, automated testing. So check in this case will run all of those three unit testing binaries that we built earlier. And I've also added in there another target called static, which in this case will run CPP check on a list of sources that we may have. So this way we can quickly and easily run the static analysis tool to make sure that we're getting we don't have any obvious logic errors in the code. So with these three things, using Make, it's this simple. We can build the code with Make, we can run all the tests with Make check, and we can run the static analysis with Make static. And as I said, this is kind of the base level of doing this. There are certainly other connections and utilities you can use to automate the procedure of also sending information to, say, a web server automatically. And there may be with build automation systems, so nightly integration systems, you can also have all of these tests run every day. You can have these tests run as a hook in your repository, so your version control. When someone checks in code, the version control system can automatically run these tests. But it take a little bit more depth than I think we have time for to go into how you would go about hooking that up to the various revision control systems. So one thing that I'm particularly fond of is a thing called code coverage, which is a way of identifying, and I was going to say identifying vaguely how well you've done with your unit test, but it's actually quite specific. I think it's a pretty useful thing. So a code coverage essentially tells you how much of your code, line by line, has been executed at least once by all of your tests. So it's accumulative. So as you run all your tests, it builds up a graph and a database of information about which parts of the code have been hit by all of those tests. And it's not perfect. It won't tell you whether you've perfectly tested your code, but it will tell you generally how well you're doing. So the procedure for getting code coverage into a C or C++ project is to compile your code with a certain set of flags which tell it that you want to do code coverage. You run all of your tests, and then you generate a set of readable statistics with one of either gcov or lcov. So gcov is the GNU code coverage utility, which I think should be available on basically any system that has the GNU utility suite installed. lcov is essentially a Perl script which wraps up gcov and produces a whole bunch of really nice HTML output, so you can graphically have a look at how well your code is covered. So let's take a look. So this is just a really simple test for code coverage. So you pass in some integer, and I'm going to run a loop for 10 times, and there's just a branching. There's an if conditional in the loop, which is going to execute a piece of code depending on what the integer we passed in is. So if we pass in 0, we're going to execute the first branch. If we pass in 1, we'll execute the second branch, and anything else will hit the third branch. So this is just a way to see how the code coverage responds. So to test this, I need to build the code with these extra flags in here to GCC. Unfortunately, the flags that you pass in are probably different for different compilers. I suspect the Intel compiler uses different flags for this. But essentially, I'm telling it that I want to use test coverage, and I want it to keep track of the function calls that are made. So to generate the stats, we then just need to run the binary that we produce, or more likely, if you're using test automation, run makecheck to run all of your tests. And then you need to run the lcov command. So what we're doing here is basically telling it to discover all of the outputs from the runs we just did. So the -c option there just tells it to discover all of the results. The directory command tells us where to begin searching, and then we just tell it where we want it to put all of the stats. The final step, generating the HTML results. So with this command, we just take the results that we produced from the previous command, and we put all of the output into a HTML directory. So it's going to have a whole bunch of things like the index.html and various pages for each of the files that are in our project. So this is what it looks like when we have finished all of those steps for that test coverage program that I showed before. You can see that it looks quite nice, and it shows you the percentages of not just line coverage, but also how many functions were covered, and also what percentage of your branches were covered. Unfortunately, it's quite a small test, so it's not that pleasing to see. But when you have a large project with a lot of different files and various branches, it's very pleasing to see all of the greens light up that you've covered a high percentage of your code. So here's looking into that particular file. You can see that it gives us some highlighted position here, where you can see that I've intentionally neglected to run this particular line in the middle there, highlighted orange. So what this is doing is showing us exactly which parts of the code have not been hit by the tests that we've written. And I think that's really very useful So as much as you may think your tests are thorough, it's sometimes very difficult to actually know how thorough they are. And this is one of a really nice way of being able to actively walk through it and determine how well you're doing. So yeah, I quite like code coverage. So one of the last things I'll talk about is test-driven development, which I don't know that I necessarily think is something that should be that I would adhere to strictly, but I've certainly found to be useful at various occasions. So the idea behind test-driven development is to use writing tests as a way to not only validate that the code is doing what it's supposed to do, but also to capture the requirements of the code. So instead of writing the code and then writing tests to make sure it works, you would write the test first and then use that to help you design how the code should be presented to the user. So the API and how it should be, what results should be considered correct. So in this particular diagram here, it shows you the what is the strict form of test-driven development, where you write a test before anything else, and then obviously that test is going to fail immediately because there's no actual code behind that test. So we move down to the diamond, which says check if the test fails, which of course it does. We move on to writing production code for that test, and then we run all the tests in the entire system. I think that's quite an important step, running all of the tests, because it not just identifies whether the particular test that you're working on is now functional, but it also checks that you haven't broken something else in the entire software suite that you're working on, which is pretty important, especially for larger software suites. And if all the tests succeed, we clean up the code and repeat the whole process from the beginning. So I guess why I say that I don't think it's necessary to perhaps adhere to this strictly is that it's not always that clear cut. I mean, sometimes you may need to write some code first and then a test, but I do think the idea of using tests to capture the requirements of your code can be very useful. It certainly helps you maintain a large set of tests, which, I mean, a lot of tests is a good thing. So yeah, here's some of just sort of enumerating the benefits and shortcomings. I think most of these I've already said, except for perhaps the two last entries on the benefits. So there's a shorter turnaround cycle for development. So by starting with tests and then designing the code to fulfill just that test, you see more results as you work through it. So instead of having sort of a big bang production where you design all of the code and then check to see if it works, it's definitely a shorter turnaround. And apparently, I wasn't too sure of this one, but apparently test-driven development ends with more modular software. So I won't go into that too much, but modular software is typically a very good thing. The shortcomings, you can end up with excessive amounts of unit tests, which leads to potentially having costly changes to lower-level elements of the software suite. So if you do have an exorbitant amount of unit tests, obviously if you make a change to an interface somewhere down low, you then have to go through and update all of the unit tests in your system to make sure that they're functional. And this is it's a balancing act in the end, I think. A lot of unit tests are good, but yeah, too many can be a problem as well. It's something that you need to consider on a case-by-case basis, I think. The last thing about test-driven development, the last shortcoming, is that it can give you a false sense of security. And what I mean by that is that while you may have a huge suite of unit tests testing all of the lower-level elements, it may lead you to believe that you can neglect some of the other levels of testing. So, for example, you may not have a lot of integration testing or even system testing, so testing that the final product actually works all the way through. And that's not a great thing. It certainly bears remembering that every level of the testing system is important. So just a short summary with which essentially I think describes my development process personally. So I go absolutely bananas with assertions. I think they're great, and there's been innumerable times that assertions have caught problems that I suspect would have taken me a very long time to find using any other method. So, and especially because they get optimized out, I think it's a really useful sanity checking method. So yeah, writing tests to capture requirements, I think that's quite useful as well, because then you already have the test there. It's not any effort to then go back and have to pour through your code and write a whole bunch of tests, which can be a very daunting thing. If you have a large code base that you've worked on, going back and writing tests for everything, it can be a very a large pain. Automating the testing procedure is absolutely essential. I mean, you really need to be able to run it quickly and easily. So adapting it to whatever build system you use is a very important step. One myth about testing, which I didn't really include, but one thing that people say is that it's impossible to test everything, and I think that's true. So while it's definitely great to have a lot of tests, it is easy to go overboard, and you can never test absolutely everything. There'll always be ways in which bugs can creep back in. Never forget to add new errors to the suite. So there's nothing more frustrating than, as I said at the beginning, nothing more frustrating than having solved a bug somewhere in the code to find out a month later that it's back in there somehow. So always add regression tests to the suite. And yeah, as I said, I like code coverage. I think it's an excellent way of having all those green lights sort of light up for you, so you can at least feel good that you've covered a lot of the code with your testing. So I think that's the end of the slides. It looks like I'm a little bit early. So it was scheduled for an hour and a half, but it looks like I'm about done. So if anyone has any questions about anything I've gone over so far, please feel free to put your hand up or post them in the question dialogue. Simon. Yep, go ahead, Simon.
Hi, Luke. I was just wondering if you're setting up testing for, say, a large C code, and in order to test the code, you actually need to do a lot of setup in the first place, like maybe create a whole linked list of array members and things like that. Is that possible within the testing framework to do that?
Yeah, so most of these testing frameworks have various levels of fixtures, which I didn't go over. I was keeping it fairly introductory, but they tend to have things called suite level fixtures and world level fixtures as well. So if you're doing an awful lot of setup that could be very slow, or I say, for example, you're populating a database, those sorts of things can be done at the world level. So you'd inform your build system, your test executable, that you'll be doing a whole bunch of setup at the start, and it'll only do it once. Is that the sort of thing you were thinking of, or are you thinking of something a bit different to that?
No, that's exactly what I was talking about. Yeah, that's great.
So I think it would just pay to. It's also, that's one of those things where it's quite different for every unit testing framework as well. They all have their different ways of setting those sorts of things up. So it depends on what you're using, but it should be possible.
Cool. Thanks.
No worries. Any other questions? Yep, Darren's got one. Go ahead, Darren.
Thanks, Luke. That was really good. I'm just wondering whether you're going to put all these resources online and maybe some examples as well.
Yeah, I can definitely do that. I guess the question is, do we have some arena or place in which to put all of these things that's sort of accessible by everyone?
maybe we'll need to make one or something.
Yeah.
But I think these kinds of things are really essential for astronomers because we're pretty hopeless, generally speaking, when it comes to coding. So not only having the notes, and that would be really useful, but actually having kind of worked examples would be really good that we could, copy, cut and paste from, and then adapt to our own code. That'd actually be a great resource to have.
Yeah, I definitely agree. And it's sort of the problem with presentations like this is it can give you an idea of what's possible, but yeah, it's very difficult to be accessible. So yeah, I think that would be good to have a sort of a tutorials library where you can get a sort of step-by-step guide of how to make these things work.
Yeah, maybe we'll work something out and announce it to everyone.
So yeah, there's been a couple of comments about using GitHub for something like that. I think it's a good idea. Something like GitHub would be useful to have sort of a suite of examples or repository of examples that could be downloaded and followed.
Thanks.
No worries. So we've had another question saying, what is the best way to test when you don't know what the answer should be? It's a really, really good question, and it's very difficult to give a conclusive answer to that. I suppose the answer that I've used in the past, which is not actually a direct answer of that question, is that I would try and be as thorough as I could with the unit testing. So each of the components of the larger, assuming of course that the application in which you don't necessarily know the correct answer is a conglomeration of smaller modules or functions, I would try and make sure that the individual functions are unit tested as thoroughly as possible to eliminate the potential for error there. And then, yeah, in terms of testing something where the answer is unclear, it really depends on the application. So potential solutions are to use a set of inputs, so modify the inputs so that you do know what the answer can be to try and test progressively more complex scenarios. Yeah, it is a good question. It doesn't necessarily have a very elegant answer, I'm afraid. Sure. So we have another question about testing GUIs such as pgplot. Yeah, again, it's a tricky one. So as I said, as briefly mentioned in there somewhere, with system testing, deciding what's correct and what's not correct can be almost as big a problem as writing the software itself. So, for example, with pgplot, attempting to write something that does some kind of image comparison or analysis may be the only way you could really thoroughly, in an automated way, test that the plots are correct. Sounds a bit daunting, though, I certainly admit. Sorry, what was that? Right. So Arm has just mentioned that there are some frameworks to help test GUIs. I must admit I'm not terribly familiar with them myself, as I've sort of spent my time with the lower levels of scientific applications. But yeah, one of the slides in there was saying that almost always someone's done these before. So I would certainly recommend having a Google search for GUI unit testing frameworks. They may not be completely automated. They may have some amount of user interaction required, but they'd most likely be quite helpful. Hope those answers helped. If there's any more questions, please send them out or put your hand up. So Greg has just asked the question, what is the best way to deal with testing in cases where large data sets are produced? So I'm not sure I can tell you the best way to handle those situations, but certainly the way that I've attempted to deal with these things in the past is to modify the testing scenario to make sure that the data produced is small enough to be manageable. So in the past, it's typically been possible, well, at least in the scenarios that I've encountered, that I've been able to modify the inputs or take a smaller subsection of the inputs, or even perhaps use artificially generated inputs to test the code in not necessarily a physically meaningful way, but just in a known set of inputs producing a known set of outputs kind of way. So I guess what I'm saying in one way to deal with it would be to artificially modify the kinds of things you're testing. But I suppose if that wasn't possible, if it's necessary to produce a large data set that needs to be tested, if you need to be thorough, then I guess as unpleasant as it sounds, you may need to have to just have perhaps two different sorts of unit testing, one in which you can test it quickly, and perhaps a longer suite of unit tests which are known to take quite a lot longer to run. So at least that way you can do a responsive set of unit testing to make sure you haven't broken anything and keep your development cycle tight. And then you can have longer tests which you can run overnight perhaps to validate that you haven't broken any of the higher level tests like integration tests or system tests. So Greg's just continuing on, is the idea to then provide small input-output data sets to go with the code base. So yeah, that's generally true. So one of the things I try and do, which I must admit is not always successful, but I will tend to try and generate the input data sets automatically. So instead of storing the data in data files and ship them around with the code base, I'll try and write fixtures in my unit tests to synthetically create a bunch of data to be run through the system. So that way, so as an example, with the Tau project, we need to query databases to extract certain pieces of information. And in the unit testing, what I would do is set up a in-memory SQLite database and populate it with, essentially, it's synthetic data, so it has no physical meaning, but it's synthetic data for which I know what the output should be. And then I'll run the code over that synthetic data and test the output from there. However, having said that, there's absolutely nothing wrong with shipping around a bunch of data with your code, a small set of data to test it with. That sort of thing happens quite frequently as well. So I think both of those methods are equally acceptable. Oh, I guess, unless, of course, there's something sensitive about the data, in which case, I mean, yeah, in that scenario, they may not be possible to ship a fully functioning suite of unit tests with the code itself. You may need to get a hold of the data in some other mechanism. Sorry. Sure. Sorry. Does anyone else have any further questions? Cool. Thanks for those questions, Greg. They are good questions. It's not always very clear the right way to prepare unit tests for scientific applications that may need vast amounts of data to run.
Okay, just for closing, thanks a lot for attending this talk. This will be our first session. This was our first session, and we are planning to run this kind of HPC and GPU webinars every 2 weeks or every 1 week if there is a demand over this. So please let us know if you think that's useful or not, and if you think that a specific topic we should be talking about, a specific examples or specific use cases that you want us to discuss. We will be happy to try to get a speaker to address these kind of issues. And also let us know if you like the tool or not we are using currently for presenting this to you. We will be waiting for a couple of minutes more if anyone got another question or something like this so we can answer it. If not, thanks a lot for your attendance.